Section 6.2 volumes. So we're going to do volumes in this section and next section. It's just we're going to teach you different ways or different methods to find the volume. So what happens is, what is the volume here? So how are we going to find the volume? Volume of what? Right? Volume of what? So first thing is we have, is to recall the formulas for the volume of some geometric shapes. For example, a cylinder, this is a cylinder, radius r, height h. So the volume of the cylinder, formula wise, it's the area of the base, which is pi r squared, it's a circle, times the height, pi r squared times the height. So what happens here in calculus, they give you a region, any region in 2D, and they ask you to revolve this or rotate it around a given line, or we call it axis of revolution. So they give you, let's say, they give you this curve, okay? And then they form a region. Let's say that's the region that we have. So this, the shaded region is the given region. Call this F. And then they say, let's revolve this around the x-axis. So the x-axis would be axis of revolution. So it's gonna go like a reflection of this, like down here, right? It's gonna look like this. So this is gonna go this, like that, right? So that's, it's gonna give you a shape, a 3D shape. And we are required to find the volume of that shape obtained. So the x-axis again is called axis of revolution in this case, of revolution, because we are revolving the whole thing about that x-axis. For now, it doesn't have to be always the x-axis, could be any axis. Now we can use the same concept from areas into volumes. So watch how we're gonna do the concept of volumes here. Okay. So the concept of volumes is we are going to take a slice, basically a slice, called like a circle, like this. A circle with radius r. And I'm gonna find the area of that circle, right? Area of that circle. So how do I find the area of the circle? It's pi r squared. Pi r squared. That's the area of the circle. And then what's going to happen is I'm going to, I took one slice. So what I'm going to do, I'm going to slice this 3D figure as we did in areas into rectangles, but here we slice into circles. Like 5 billion circles. If you stack 100 papers on top of each other, you're gonna see a stack of paper, right? There's gonna be a thickness. If you put 1,000, you're gonna get like a bigger height or thickness, right? So same thing here. If you bring a circle, like a piece of paper, circular shape, and put like 20, 50 on top of each other, start adding more and more, you're gonna get a height, right? You're gonna cover. So to cover that shape, we slice one circle at a random place within that figure, and then you're gonna slice one below it, and then another below it, and one above it, above it, above it. So all these circles you are slicing, they're gonna cover the whole shape. So basically, I'm gonna add the areas of all these circles, right? All the areas of these circles. So how do I do this? It's gonna be adding the integral from, I don't know, in general, A to B for the volume, right? And if, let's say I'm doing dx, because I'm slicing on the x-axis, right? So this reminds me of the volume of the cylinder, pi r squared times the height. The height is like, say, the dx, right? So now, watch. In general, we always put the pi out because it's a constant, the integral from A to B, and the radius here, if you look at the diagram one more time, see, look at the diagram. This is the radius. This radius is the same as f of x. If you pick any x value, That's f of x. So then I can rewrite this pi the integral from a to b of f of x squared dx. That's the volume. That's the volume of that figure, or the area, or the formula to find the volume. Now that circle that I found here, we call it disk. We call it disk instead of area. A disk is a filled up circle. That's what it is. So now, in this case, we call this disk method. Using disk method. In disk method, keep in mind that the rectangles we draw, they always must be perpendicular to the axis of revolution. Now that was just one function f. How about if we have different functions? So how about if we have, as we did in areas, let's say we have this one and this, say this is f, this is g, and this is the region, and I'm gonna rotate this, let's say, about the x-axis. How do I set up the integral to find the volume? So you're gonna get, you can reflect it here as we did before. Then the volume would be pi the integral from, say in general, a to b. Now when you draw the rectangle I was talking about, you draw a rectangle like this. It's perpendicular to the axis of revolution, which is the x-axis here. So you draw a vertical rectangle. If the axis of revolution was the y-axis, you draw a horizontal rectangle. Now I need to know how to deal with this one. So in this case, we go about the rectangle has two sides. One the top one, the bottom one. The top one, this is the further one from the axis of revolution. I'm gonna call it capital R. This is the closer one to the axis of revolution, right? So what I'm gonna do is I'm going to find. To do that, I'm gonna find the volume by squaring f first, dx, and that will give me everything including that white space in the middle, and then subtract the volume formed by g of x when rotated about the x-axis. So that will, so what I'm doing is we are finding the volume of this whole shape minus the one to give me that volume. And that's like a dome, you know, like you have a dome, you want to find the volume dome, there's a space in the middle. So what you do, you find the volume of the whole thing minus the volume of the space. That will give you the volume of the dome. Make sense? So that's what we're doing here. So we always can rewrite this as pi integral from a to b f squared of x minus g squared of x dx. And this is called washer method. Washer method. Let's look at an example, first example. Let's say find the volume of the region obtained by find the volume of the solid, not region. Find the volume of the solid obtained by revolving the region bounded by the graphs of y equals x squared, x-axis, and x equals 1 about the x-axis. graphing wise should be very easy. Say x equals 1 here. This is the region, and I'm revolving about the x-axis. So in this case, the volume would be pi. Don't forget the pi. We draw a rectangle perpendicular to the axis of revolution. So there's a dx, right? So the equation of the function is x squared. So remember, you need to square it, dx, using disk method, right? And then the integral should run, or the rectangle should run from 0 to 1. And now this such integral is easy to integrate. This is x to the 4 dx, and this becomes x to the 5th over 5 from 0 to 1. So the answer is pi over 5. If we rotate the same region about the y-axis, we need to find the volume of the solid obtained. So the same region, I'm going to redraw it here. Y equals x squared. And now we're revolving about the y-axis, right? So here the rectangle must be perpendicular to the y-axis, so we have a dy. Now notice there's a space. So there's a space between the region we're trying to revolve and the x-axis, the axis of revolution. You see the space, the white space? So that reminds me of Washer method, right? Washer method. So Washer method said, to set that up, you go volume, pi, integral. See the y, the y, watch how we do this, how we set it up. We go, this is the axis of revolution and the rectangle. The further one is this, that's, we call it the outer radius. And this one is the inner radius, outer radius, inner radius. So how do I find what capital R is? That's the distance from 0 to 1, which is 1, right? That's the distance 1. So 1 square minus the parabola, right? The parabola. But remember, we're going to have dy here. So I can't put x squared squared. So I can't put x squared. So what I do, I solve for x, which is square root of y. So I'm going to put square root of y squared. Now y is changing from 0 to that point, 0 to 1. Because if you put x1 in this function, y is 1, 1, 1. Right? This point is 1. And then it becomes easy to integrate here. First, you square this is 1, and that's y dy. And then keep the pi out. The integral of 1 is y. Integral of y is y squared over 2, from 0 to 1. Plug that in, you get 1/2 minus 0, so that's pi over 2. Next example. Let R be the region. Let R be the region bounded by the graphs of y equals square root of x, y-axis, and y equals 3. Find the volume. Find the volume when R is rotated about, let's call it part A, x-axis. Okay, so the graph is going to look like, this is y equals square root of x, y-axis, and y equals 3. Say y equals 3 this. So this is the region here, and it's about the x-axis. So I have to draw a vertical rectangle. So I have dx. So the volume would be washer method, washer, pi, integral. That rectangle is moving from 0 to that point, wherever the graphs of y equals 3 and y equals square root of x intersect. So we set them equal to each other, square both sides, so that's a 9. So from 0 to 9, okay, dx. So the further one from the axis of revolution, this, which is 3, that's 3 square, minus the other one is this, which is y equals square root of x. And then I'm sure everyone can integrate this one. You would get 81 over 2 pi. Let me add another part. How about if we do about the y-axis? Same region, but about the y-axis. This is y equals that, and this is y equals 3. Again, I'm redrawing. But this time we're doing it about the y-axis. That's the axis of revolution. So we have to draw a rectangle perpendicular to the axis of revolution. See, there's no space now between the region I'm revolving and the axis. So to find the volume, you start with the pi, the integral. That integral is going to go from 0 to 3, ranges from the bottom up, 0 to 3, and then 0 to 3, and then to set that up, it's just you want to find the distance from here to here. What is this? That's the y equals square root of x, right? But notice I'm going to have a dy because of the rectangle, dy. So if I square both sides, I solve for x. So it's going to be y square square. That x equal y square square. And then you can easily integrate this by first expanding or multiplying that and finish it up to get you 243 pi over 5. I'm going to take the same region, but I'm going to rotate it around y equals 3. I'm redrawing the region again, y equals square root of x, y equals 3. We label everything, and we're taking this region about y equals 3. So remember, we draw a rectangle perpendicular to the axis of revolution. Right? Our goal is to find this, that distance, right? That distance. That's the radius. That's the radius. Because think about it, if that's the case, this is gonna come up this way and down, like, then you got the 3D figure like that. Do you guys see it? So the radius is just the length of that rectangle. That's what R is. I want to find what that is. So to set up the volume, we start pi. Again, the integral is going to go 0 to 9, 0 to 9. And what am I going to have here? So I'm going to have a dx at the end. The length of that one, watch how I'm going to find that. It's going to be the whole thing, which is 3 units, minus this one, which is y equals square root of x. So it's 3 minus square root of x, and you square it. 3 minus square root of x. And then it's so easy to integrate. How about if we do y about y equals 4? Say this is y equals 4. So I'm rotating around this, let's say. Or we could bring it down if you want a little bit. This is y equals 4. So how are we gonna do this? Again, the rectangle must be perpendicular to the axis of revolution. So that tells me there's a dx, right? Dx. So the volume is gonna be pi. Integral. Again, it's gonna go from 0 to 9. 0 to 9. Let's see what we have. There's a space. Do you see that region? The shaded and the axis, there's a space. So we're gonna use washer. So washer means you're gonna have something square minus something else square. Right? So let's see how do we go about this. The first one is this tip from here to here. What is that distance? Well, it's a little bit tricky. That distance is gonna be 4. Look, that distance from here to here is gonna be the whole thing 4 minus the function itself. The whole thing 4 minus the function, that gives me the square root 1. So 4 minus the square root of x for the first one. Watch the other one, the other tip of the